we are probably we're going to start, but probably not finish talk on the convergence of the campbell-hausdorff formula. We start off with the theorem, which just states, sorry, one sec. We're going to be in characteristic 0 first off. And we're going to let G be a finite dimensional Lie algebra over K. Then G is the Lie algebra of an analytic group chunk. So essentially this is saying we can go, like, we know already that we can go from a Lie group to a unique Lie algebra by looking at the tangent space at the identity. This is saying that for any Lie algebra, we can go backwards and find an associated Lie group. In this case, that alone isn't enough to make the group you find unique, unfortunately. There is a restriction. I believe it's unique if it's like, if you require the group to be simply connected as a manifold. But otherwise, yeah. We're just showing you can go backwards here. In proof, we're going to let n be the dimension of G. Don't know why I put period. That this is kind of like a function or something. And we will use the Campbell-Hausdorff formula to define a formal, that is nothing what I just wrote, a formal group law in n variables such that first off, F is convergent. Secondly, G is isomorphic to the Lie algebra K to the n under the bracket defined by this group law. Okay, so for step 1, we pick a basis for G in n variables, of course. Then there exists unique, I don't know if I showed this before, the idea of structure constants. Such that the bracket of an xi and xj, essentially just each component in it is given by gamma I j to the h, where h here too is just an indexing constant. So essentially each one is just the appropriate, is how much each gamma h of ij is like how much the h component is present in the bracket of I with j. We then define gamma to be, these are also can be thought of as like variable O being over x1 and xn to be the maximum of the size of each ijh. Note our change of basis by multiplication by a non-zero scaling factor lambda, where gamma ijh over our new basis lambda x1 through lambda xn is just lambda times xij to the h of x1 through xn, and likewise gamma of lambda x1 through gamma xn is lambda of gamma, is the absolute value of lambda on gamma. My gammas look too much like y's. Why did I call it x there all of a sudden? That's weird. It's gamma. Lambda of x1 through xn. Alright, step 2. Going to let, that's bad Roman numeral, but whatever. Let R be the formal power series of k over x and y, which of course we can split x and y into x1 through xn and y1 through yn. And we let E to be r to the n. And then corresponding to the basis x1 through xn of g, we define a Lie algebra structure on E by the bracket of some fi and some gj, of course. We don't need these indices to match up. And this is going to be the sum over our i's from 1 to n, and also over j from 1 to n, of gamma ij to the n, ijh, to each component fi and gj of our, why did I do a comma? Gj over these sequences. Because these two on the left, I should say, are sequences over our, where each one is an element of R. Now we want to consider the adjoint of x and the adjoint of y, with x consisting of components x1 through xn, and y consisting of components y1 through yn. Then we say that P consisting of P1 through Pn in E is a homogeneous polynomial of degree R if each Pi is a homogeneous polynomial of degree r. And we let the absolute value of p be the maximum of the absolute value of the coefficients of the pi. This gives us a lemma. Suppose P and E is homogeneous of degree r. Then if z is x or y, the adjoint of z on P is homogeneous of degree r plus 1, and we have the absolute value of the adjoint of z on P has an approximation being at most n squared gamma times the absolute value of P. And for the proof of this, so we're going to consider z equals x with the adjoint of x on P being q1 through qn, and we let pj be each pj be the sum of aj sub alpha beta times x to the alpha, y to the beta, and corresponding qh to be the sum of b sub alpha beta to the h, just being another index as always, times x to the alpha, y to the beta. Then we can also rewrite QH as being the sum of gamma I j to the h times xi p sub j. Hence each QH is homogeneous of degree r plus 1. That's difficult to read. R plus 1 and b sub alpha comma beta to the h is the sum over I time and over j from both from 1 to n of gamma I j to the h of a to the power of j and indexed by alpha minus delta I and beta. Thus g sub alpha beta to the h is at most n squared gamma times p as desired. And this comes with a corollary. Where z is x or y, R be be non-negative. And then the adjoint of Z on M to the R on E is within M to the R plus 1 E, where M is the maximal ideal of R. This is an immediate corollary. Alright, and now we're on to step 3. We're probably going to have to split this whole proof up into a couple videos because it's very long, but we're going to let S be components X and Y. Set the two elements and consider the free Lie algebra LS on S and its completion, which you recall is L hat of S, defined to be products from 0 to infinity of L sub S to the R. Let theta be the canonical Lie algebra homomorphism from L sub S to E, such that X bar goes to X and Y bar goes to Y. Then we have the second lemma, where for positive R, theta on L sub S to the R is within M to the R of E. This is immediate by our previous corollary. And we get from this, we know theta extends uniquely to a Lie algebra homomorphism of the completion of our free Lie algebra into E. Now let Z bar in the completion of the free Lie algebra on S be the unique element such that e to the x bar times e to the y bar is equal to e to the z bar. And we let f be theta of z bar. Then, as seen, first off, f is a formal group law in x and y. B of x and y is 1/2 of the bracket of x and y. And this gives us, of course, that the f bracket of x and y is 1/2 of the bracket of x and y minus 1/2 of the bracket of y and x, which is, of course, just a bracket of x and y. This motivates another theorem, which just says that f is convergent And this will need lemmas. The sum over P1 through PM and across Q1 through QM, with each Pi plus its associated Qi being at least 1 and M being at least 1 of T, some variable B, to the sum of the P's plus the sum of the Q's converges for small t. Proof, we can write the above as the sum across all m's from 1 to infinity of the sum for P and Q being at least 1 of T to the P plus Q to the M. For T less than 1, the inside term converges to we'll call it alpha being 1 over 1 minus t squared minus 1. For small t, alpha is then going to be less than 1. You can work out what the value of t would have to be there. Then, of course, the sum of m equals 1 to infinity of, it's going to work out to be alpha to the m, which as we know is 1 over 1 minus alpha, will converge. Well, this converges to be equal to the right hand side when alpha is less than 1. Alright. Yeah. And so we'll finish our setup here, I think, and then we'll prove our two main theorems next time, probably. So lemma for exists a constant alpha being between 0 and 1, it could be 1, such that each n factorial is at least a to the n, and the size of n is at least a to the n for all n being a positive integer. Now the proof of this, in case A, where k is Archimedean, well, we can just have, of course, alpha being equal to 1, we'll trivially solve this, and likewise, k is ultrametric, and restriction of the absolute value to the integers is trivial. In which case, we can take I switch between a, what they called, and alpha. Let's just have it be alpha. Anyways, in the second case, we can take alpha to be 1, as you do. Case C, k ultrametric, and the restriction of the absolute value to the rationals is a p-adic absolute value. First, note the second inequality is by the first. Since we have the absolute value of the factorial of n minus 1 being less than or equal to 1 for all n at least 1. Then we take alpha to be the absolute value of p to 1 over p minus 1. We have on a new page that the size of n factorial is at least e to the n, being equivalent to saying that our p-valuation of n factorial is at most n over p minus 1. However, the p-valuation of n factorial is square bracket of n over p plus n over p squared, and so on, which is at most n over p plus n over p squared, plus so on, which is a geometric series, so this is just n over p minus 1. So we get that n factorial is at least alpha to the n. And this is all the setup we need to prove our two theorems. Well, there is one more lemma, but it's in there. So I don't know, I always seem to make these videos, my third videos now, shorter, but we will call it here mainly because it's late, I've got other things, so we'll call it here. Thanks for watching.